Okay, I think we're good. All right. Thank you everyone for joining us today. We're going to learn about linear regression and classification with Brian. As you know, the reactors are hubs for founders and developers to connect and learn about all the latest technologies. And today's session will be part of the regular weekly workshops that we do on diverse topics to help you understand everything you need in terms of data science, machine learning, AI, and so on. So please be part of the communities that we have across the world. These workshops are shared across the EMEA, so you might be joining us from London, Stockholm, Tel Aviv, or Abu Dhabi, or anywhere in between. So welcome to the Reactors community. All our programming is free and open to all. We're doing these live streams online, and they're recorded, so they will be available to you later on the YouTube channel. I'm gonna send that link to you in the Q&A tab. And during the workshop, please keep the Q&A tab open. This is where you can send us all your questions, and we're gonna discuss them with Brian today as well. I don't want to take more in this introduction. I want to hand over the mic to Brian to start the session. And whenever you have a question, please shoot it through on the Q&A. And Brian, let me know when you want to have these questions answered, and I'm going to bring them up to help you out. I'll be in the background during the session, so see ya.
All right, thank you very much. Can you hear me?
Yeah, all good.
Okay, great. So welcome everybody. Sorry about the delay. Today we're going to talk about some of the more fundamental approaches to learning from your data. Specifically, we're going to talk about linear regression and classification, which are two types that allow you to find if there are linear relationships within the features that you're trying to learn from. It's a very well understood and efficient and generally easy to explain machine learning activity. So hopefully you'll find that interesting and useful. My name is Brian Sletten. I'm an independent software consultant. I've done a fair amount of machine learning training around the world, and very happy to be able to reach out to you from where I am in Northern California, which is very early. So I apologize if I sound a little tired. There will be a survey that we'll put a link to at the end. Please do provide your feedback. But otherwise, I'm going to now switch over to Visual Code. So if you go to the Microsoft Reactor's GitHub account, which I will do right now just to show you where to go to find everything, there is a ton of material there, but we're going to focus on specifically in the workshop resources directory. There is a data science and machine learning directory. In there's a data science 2 directory. And in there's a bioscience project, which has an instructor and a student notebook. I'm going to walk you through the instructor notebook just because we don't have a whole lot of time today. But hopefully you'll go back and spend some time going through the student notebook and trying to recreate some of the things that we are trying to do. So again, that's github.com/M or /Microsoft/R reactors, workshop resources, data science and machine learning, data science 2, bioscience project. So in there that we have a couple of Jupyter notebooks, and I'm going to have to assume that you have been exposed to Jupyter notebooks and some of the basics of Python. I'll try to be clear as I go through, but at this point there's some other material through the Reactors program you can catch up on if some of this is unknown to you. So a Jupyter notebook is a great way to sort of tell a data science story, and it allows you to mix in documentation and code. And so the underlying notebook itself, as you can see, can be checked into a repository with data. The data directory underneath the bioscience project one has a couple of comma-separated value files. These are spreadsheet files. And when we run within, say, VS Code, relative to that directory, if you just open up that directory with the notebook in it and then select the IPython notebook, you'll be able to hopefully follow along. Okay, so in this example, we're going to look at some data and explore it from a linear regression perspective. If you have done this before, you'll recall that one of the first things we need to do is make sure that we have NumPy and pandas. So NumPy is a framework that makes Python available to have very high numerics performance. Otherwise, the typical dynamic nature of Python makes it rather unsuited for this kind of work. And then pandas gives us the ability to sort of read files in as data frames and to manipulate them to pull out certain columns and rows and whatnot. So we're going to use that to read the data in. We're going to import matplotlib pyplot, which is a set of functionality for drawing out graphs, which we are going to use as part of our exploring the data process. And we're going to use a three-dimensional axis for one of the final examples. Now, when you run in Jupyter Notebooks, it's actually running the code in a background process and then returning the results. So you have to give Jupyter Notebooks a hint that you want to see the plots rendered in line. And so this magic directive %matplotlib will make it so that when we use matplotlib to draw some of our diagrams, they will show up within the notebook as output. So I'm going to execute that cell, and you may notice that it became an asterisk for a couple minutes or a couple seconds, and then became a number. That just lets you know that the execution of the cell is done. This particular one doesn't have any side effects, so we don't really see anything. But at the beginning of the cell, there is beginning of the notebook. There's a quick walkthrough to help explain to you a little bit about what's going on. So we're going to use a data set from a article, the source of which is linked here if you're interested in reading it. And it allows us to explore the relationship between the mass or the body weight of a mammal and its brain, just to see if there's some kind of connection between them. So this particular data set is available as the file mammals.csv in the data directory. So if we use the pandas read CSV functionality, it will read it in and make it available as a variable in a data frame, as a data frame. And then one of the first things that you do with a data frame is usually to call the head function, which will tell you something about the structure of the data that you just read in. So in this case, we have a column called mammal, which tells us the name of the mammals that are at under consideration. Then we have the body weight, and we have the brain size, the brain weight. And so what we would expect to see is that there would be some kind of relationship between how large an animal is and its brain size. And if you find yourself having the kind of relationship that says the more of this, the more of that, that's a pretty good sign that there is a linear relationship between those features. And so that, again, that makes sense, right? If you are very tall, that height may be spread out through like your torso length or your leg length, but in general, the taller you are, the longer your legs are going to be, right? So we would expect there to be that kind of relationship going on here. So we're going to start with a visual exploration of the data. As you're doing data science, you're usually doing so within kind of a workflow, and the workflow generally involves acquiring the data, loading it in, and then exploring it, because you want to know roughly what the shape is. if that shape isn't what you expect your general population to look like, then there's going to be trouble with the analytics that you derive from the data that you're looking at, right? So you have to make sure that it looks like what you're expecting. Otherwise, the data could be skewed, and that will impact the analytics. We tend to be fairly visual creatures, and so one of the first things that we can do is to visualize the relationship between the features of body size and brain size. And so here we have a measure of, I forget the units here, probably says up here. Nope, just body weight and brain weight. So, weight in kilograms and brain weight in grams. Okay, so right away we see that we have a bit of an issue potentially, because with mathematically related features, you often want to make sure that the data looks similar, has a similar value space, uses similar units and things like that. And so what we can tell very quickly here is most of the data, when we visualize it, is in the lower left corner, so closer to 0. But notice we have a couple of very big animals, obviously in this case probably whales, as one of the largest mammals, or the largest mammal that's out there. And so there's a big difference between the values, and that often causes trouble with us for linear regression kinds of systems. So one of the ways that you can do that is to actually transform the data in a way that makes it so that vast range of variance in the values of the data isn't quite as pronounced. And if you remember back from your high school or uni experiences, you might remember talking about logarithms. And so one of the things that we can do is to, before we visualize the data, transform it in a way that says apply logarithmic transformations, so that things that are growing seemingly exponentially will not look the same way. So when we re-render the scatter plot with a log transformation on both sides, you'll now see that we're going from 10 to the -2 up to 10 to the 4 here, and 10 to the -1 up to 10 to the 3 there. And so each unit that we go over is 10 times as large, but you'll notice that the data is spread out more evenly in that space. So this big little gap right here represented a much larger gap before we did the transformation. And so now we can see that there is what looks like a linear relationship to the data. It's just kind of hidden from the fact of that there was such a wide range in the value space. So, by the way, Hassan, anytime you want to ask questions, feel free to interrupt if there are any. All right, so this is a useful transformation to help us with our visualization, but we're also going to have to remember going back and forth between the raw data and this transformed data, and perhaps back again, when we need to reverse perhaps the log transformation of the data through the exponentiation function. But this gives us a value space in the transformed data that is much more conducive to something like a linear regression analysis. So even though the original data is being modified in the process, we have the ability to analyze that process data as well. So in order to do that, we're going to make sure that we do our training on transformed data. So in this case, we're going to call the NumPy log function. We're going to pass in the pandas series. So the data frame is in the variable mammals. There is the column body. We're going to pull out that column as a pandas series. We're going to turn it to a NumPy n-dimensional array and just reshape it so that it's fitting the way that our learning algorithm is going to expect. It's going to expect us to have a column, one or more columns of data representing each of the features we're trying to learn from, and then each row will represent the individual mammals under discussion. So this is just a fancy way of transforming the data. And if you're not familiar with NumPy well enough to know what's going on, I encourage you to create sorry, let me turn off notification there. Create some new cells and try to do this one at a time. So what you can do is you can create a new code cell and say, let's just look at the this portion of it. So you can say copy. So in this case, you can say, okay, this is giving me the series, and then if I take the np.log, oops, mammals body. So if you take the log of that, this is going to go ahead and apply the logarithmic transformation to each of the data elements. So if you just do this one at a time and sort of see the results, I think that will help you understand a little bit more about what's going on. But in general, what we're trying to do is we're trying to set up a supervised learning activity, which generally says to the learner, here are my inputs, and I would like you to find the relationship to the outputs. So it's traditional to refer to the inputs as X and the outputs as Y, but you may also hear it as features and target, or inputs and outputs. So they all mean the same thing, or the data and the labels is another way that you might hear it. So in this case, we're going to transform the body weight in kilograms, and we're going to transform the body weight or the brain weight in grams. And so what we're suggesting is, based on the visualization that we saw, is that there could be a linear relationship between the two. And so we're going to try to let it figure that out. Now, it's not usually the problem with linear data or linear regression modeling that you have the ability to overfit the data as much as with some of the more flexible models, but that is something that we're still concerned about. And what that means is, if the model pays too much attention to the input data, it may just end up memorizing those details mathematically, right? It may just say, oh, this data is connected to this output this particular way because that's what you told me. And that's a concern, because when you try to make predictions off of this using data that you haven't seen before, then it's not going to do a good job. And so one of the ways that we can detect if we're overfitting is to break the data up into training data and test data. If it does well with the training data, but it doesn't do well with the test data, that's usually a good sign that you're overfitting. It's like a child who finds the answer sheet to a test, right? If he memorizes the answers to the test, he will do very well on the test. But if you then give him the final exam or ask him different questions, it'll be pretty clear he didn't actually learn anything. And that's the situation we're trying to avoid. So NumPy has this, scikit-learn has this useful train test split function. If you look back up at our imports above, you'll see that we pulled in train test split from the scikit-learn model selection package. This is a function that will go ahead and shuffle the data for us and then split it up how you want it. So we're just going to say I want the test data to be roughly 30% of the training data. So if we had 100 rows, then 70 of the rows would be randomly chosen to be training data, and then the remaining 30% are going to be our output, our test data. So what we then do is we will train off of the inputs and the outputs of the training data, and then plug in the inputs for the test data. That will give us our predictions, and then we'll measure how we did with the predictions against the actual test output data and see that. So we're transforming the body weight logarithmically and then shaping it so that scikit-learn will know how to find it. We then transform the brain weight We split it up into training and test data. This returns a tuple that we're destructuring into the X training data and the X test data, the Y training data and the Y test data. In the linear package, so again, let's look at our imports. In the linear model package of scikit-learn, there's a linear regression estimator, is what they call it. This is a learner that's able to find this kind of linear relationship in the data. So we're going to create the instance, and then all of the learning magic happens in the fit function. So you can generally tell whether something is a supervised or an unsupervised learning activity by looking at the number of parameters to the fit function. If it's X and Y, then it's a supervised learning activity. If it's just the X data, then it's probably an unsupervised learning activity. So let's go ahead and run this. And at the end of this now, we have a model that has been trained, and that model has absorbed what it can from the inputs and the outputs of the training data. So what we're going to do is we're going to go back and we're going to plot our original XY data points, and then we're going to plot our predictions, right? So the reg variable represents our regression model. It's been trained. We're going to plug in the X data. So in this case, X is our input, sorry, excuse me. And then we're going to do the reverse transformation to project it back into the same value space. So when we run that, we will see that the original data points with their logarithmic transformation are in the blue, and the red line is the line that we have learned from this transformed data, projecting it back into this transformed space. So that's quite a good fit, it looks like. You can see that the data sometimes is a little bit above the line and sometimes is a little bit below the line. The error between what's predicted and what's in the actual data is what we would say normally distributed around the line, which is generally a requirement for linear regression to do a good job. But we want a little bit more confidence than just, hey, it looks right. So there's a measure called the R squared score, and it is a measure of how good the variance in the input data is explained by this relationship. And so there's another function that we pulled in from above called the R2 score, and if we run this function over our test data and our predictions, so again, roughly how close is the model at predicting the actual test data? Well, we take our X test inputs, we run it through the prediction model that has been trained off of the X train data that makes suggestions of what it thinks the Y value should be, and then we compare that to the actual Y test data. And so we see that we have about 87.5% of the variance in the original data set is driven by the body size. So there is a pretty strong linear relationship between the size in weight of a mammal and its corresponding brain size. Now, why isn't it 100%? There obviously could be other factors. And so since we're only looking at one other feature, it seems to suggest that other features would be able to perhaps help us improve our prediction abilities. So we're going to now plot the body and the brain weight and see that when we project back to the original space, this is the logarithm of the X array, but then we're exponentiating it back into the original data space here. We can see that there's this curve in the predictions, and that curve is in fact because the outliers are kind of pulling it into a slightly different shape. the outliers have a strong impact on this, and they're also outsized relative to the other one. So that's where some of the noise in the data is coming from, is because of this huge variance in the value space. But the fundamental thing about a linear regression is that we're able to take some data, use the data to find the parameters of the line that we believe exists based on the visual exploration of it. And that line can be represented with the equation of line that many of you probably learned in high school, y equals mx plus b or c, depending on where you are. So the actual relationship here is that the intercept plus the coefficient times the x value equals y. So that transformed relationship that we saw made it easier to see, but we see the basic nature of the relationship here as well. So the thing that was learned by the linear regression algorithm is the coefficient and the intercept of the line that it's evaluating. With scikit-learn, the things that it learns are stored as attributes with trailing underscores in their names. That's a way for you to know that this wasn't an input parameter, but this was a learned parameter. And so the coefficient, you'll notice, is actually an array. And it's an array because had we trained on more than one input feature, then there would be a separate coefficient between each feature and the output. Basically, how strong of an impact does this feature have on the output? And so we see that for our particular case, the relationship is such that the coefficient is 0.77 roughly, and the coefficient is 2.13. Now, why is it those particular numbers? That has to do with the shape of the data. It's not always easy to explain the exact details there. The more important thing is just to notice that the parameters of the line do a reasonably good job in the transformed logarithmic space of predicting the relationship between the inputs and the outputs. Now, a linear regression is usually a good place to start, particularly if you have reason to believe that there is a strong linear relationship in the data. But it's not always the right choice. Depends on what it is that you're trying to do. And for an example of that, we're now going to load in some data from a different data set. This is from a different study, and it's a survey of statistical work on the Mackenzie River series of annual Canadian lynx trappings for the years 1821 to 1934. So basically, this data set has historical trapping data in it. So we're going to read in a different CSV file from the data directory, and then we're going to plot that out. And what's interesting, the plot function will try to draw the line between the points. If I just read this in and did a scatter plot of that, oops, sorry, that's not the right. I'm not going to worry about that right now. Anyway, the point is each of the x values and the y values are being plotted on here, and then it's drawing the line between the individual points. And what that shows us is there's quite a good cyclic relationship between time and the count. And that's not something that you necessarily would have considered or expected, but biologically, it seems to be suggested that when there's enough food, the population grows somewhat out of control. When there's not enough food, the population thins out. Either the animals migrate and move someplace else, or less fortunately, there's just not enough food for all the mammals. So the reason that's not good for a linear relationship is because the data varies so much. Notice that trying to represent the data with a line is going to miss all the up and down variance, and therefore a linear model would be a poor predictor for this kind of relationship. Now, notice if the data is trending up, then what you might want to do is to try to regress on the average value or the median value, and maybe over time you'll see a trend in it, and that would be useful with the linear model. But in general, cyclic data is not necessarily a useful thing to do with a line. Now, that's not to say you can't try. So we will grab our yearly data and shape it in the way that scikit-learn is expecting, so that we'll end up with one column of data. And then the count will come from the links column, which is one of the columns that we read in with our recent data frame. We're going to split this data up with similar proportions, 70-30, create the linear regression, fit it, and then plot out the results. And so again, you can see the line. These points pull the line down. These points up here pull the line up. In general, it seems like there's maybe a slight uptick over time. Maybe changing climate in the area, allowed for more lynxes to thrive in the same space over time. I'm just guessing. I'm not a biologist, but notice that catches the trend, but isn't a good predictor for the individual points. And one of the ways that we could measure that is to try to make predictions here and see how well they match up to our actual test data, and then check our squared score, and we'll see that with a score of negative 0.017, this is not a very good predictor. So oftentimes it will be fairly obvious, visually when a line is doing a good job, but the shape of the data and the variance within the data and the cycles within the data are all things that might force you to pick a different model. So, you might pick something that has more of a polynomial, sinusoid wave or something, right, as a way of representing elements of this. And with a very high order polynomial, you'll be able to represent the variance pretty well. The concern would obviously be whether that's too expressive of a model to work with the data, and you may just end up overfitting it. So, all right. And the good thing about things like the R squared score is that it's a way of keeping track of how well you're doing in an objective way, right? Just looking at the line, you may say, okay, that looks pretty good, but this is just a measure of objectivity. So with our body to brain weight relationship, in the logarithmic space, we saw a very nice linear relationship. In the cyclic variation in the number of lynxes over time, it was a much worse representation. So linear regression is only one part of the story. Another part of the story is classification. So generally what you're trying to say here is data that you've shown me in the past makes me think that this data that I'm now seeing in the future suggests that it's like these other things that I've seen in the past. So you're trying to classify elements based on maybe how they've been classified in the training data set. One of the most common early data sets to use with the scikit-learn experience, or pretty much any machine learning experience, is called the iris data set. And it was established by Ronald Fisher in a 1936 paper. And the idea was, by looking at the physical characteristics of a sample set of irises and knowing which class of iris they belong to, there are three classes. One is called setosa, one is called versicolor, one is called virginica. By looking at how the sepal and petals, the physical features of the irises vary, you may see some consistency. So maybe all the setosas look one way, all the virginicas look another way. And then if you trained a learner on that, then they would be able to look at a new iris that they'd never seen before and have a pretty good chance of guessing what it was. So let's load the data in. This is a data set that ships with scikit-learn. I always like to say, if you are a parent and you have children, you've learned that birthday gifts and whatnot that require batteries better come with the batteries. Otherwise, it's going to be no fun. So a learning tool, machine learning tool, better come with some data to learn from, because not everybody who's learning has interesting data sets to dive right in. So there's this function called load iris, and that's loading the data in a way that scikit-learn is expecting it. So we don't have to do the same kinds of transformations that we did, that you saw with the pandas data set, which we loaded in directly from a comma-separated value file. In this case, it's stored in a way that it's already expecting. So it's called a scikit-learn bunch. It's not a pandas data frame. But notice we can just say, okay, our X data is the data portion of what we read in, and the Y data is the target. So our inputs and outputs are already split up for us by the scikit-learn toolkit. So then once we have it in that form, it's easy to put it into a pandas data frame by saying the data frame gets its data from there and its columns from the feature names of the scikit-learn bunch. So in addition to iris.data and iris.target, there's iris feature names, and that's the name of each of the features. So let's go ahead and do a head on our iris data frame after we load it in, and we should then see what things look like. So we see now we have 4 columns: sepal length in centimeters, sepal width in centimeters, petal length in centimeters, petal width in centimeters. And if I add a column here, I can say, let's look at the Y data. And you'll see that that is a collection of values ranging from 0 to 3, representing the 3 classes of the data set. So there's 150 samples. A third of them are setosas, a third of them are versicolors, and a third of them are virginicas. So what we're going to try to learn is the relationship between these features and which class they're in. And once we do that, then we're going to maybe be able to make good predictions about data that we haven't seen yet. So one of the approaches we could take is to use what's called a k-means clustering. And in this case, it's just using a geographic or geometric relationship between the values to find which ones are close to each other, in essence. So we're going to tell it how many clusters we want to see, because we know that there are 3 irises. It takes no great leap to say we want 3 clusters. If you didn't know the data set very well, though, changing this parameter would force it to find more, or fewer or more classes, and those classes may or may not be meaningful. So this is what's called an unsupervised learning activity, and as I indicated earlier, you can tell because the fit function only has x's and no y's. Now we would love it if we could just say all the time, here's our data, tell us about it, but generally the only thing it can tell us is what's already in the data. And so things like how close the points are to each other is an easy thing to learn from. So in this case, we're going to say, try to fit the data sets into 3 separate clusters, and then we're going to make predictions of the X data. Where do you think the cluster should be? Now, this is not necessarily how you'd normally go about this, because we don't know with a k-means clustering whether the clusters are any good. But if we just take our X data and fit on it, and then make predictions off of what's generated, we can see that the accuracy is actually pretty low in the classification. And in part, we're not using anything about the actual features of the data relative to each other that we could use for predictive results. So in this case, we're going to use a separate classification algorithm. It's called the k-nearest neighbors. Now, there's, again, this parameter k, but it serves a different purpose. With the k-means clustering, that was the number of clusters we expected to find. With the k nearest neighbors, it's how many of your neighbors are we going to consider when determining what you're like. If the k is set to 1, then whichever data point that is closest to you will be considered the driver in the decision of what we think about you. If I set k to 2, then the 2 closest neighbors will be considered. Maybe I'll average out the values between them. So what you can see with this algorithm, we are not starting with a random element like there is so much with the k-means clustering. We're actually looking at the data and saying which data points are the most like other data points, and then use that information to make predictions. So if we compare you to things that you're more like, that's probably going to be a better job of comparing you, being able to predict what kind of thing you are. For example, if I compared you to everybody in your organization based on age, I may not get good predictions, but if I compared you to everybody in the same job title, so all the junior developers, all the senior developers, all the executives, chances are I would make better predictions. So what k-nearest neighbors is trying to exploit is the similarity between one set of data points and another set of data points. In this particular case, the data points are talking about the physical characteristics of the irises. So we're going to try to find irises that have similar physical features, and then say other irises that are close to those are probably of the same type. And so what we have here is a knob, and the knob is called k. It's a hyperparameter that changes the sensitivity of the learner from the influence of one or more data points. If the knob is set low to 1, then the closest neighbor, as I said, has the strongest influence on you. As you increase the knob, then we reduce the impact of the original neighbor, and we start to spread the influence around the other neighbors. And if I crank it all the way up to the maximum value for k, which is the size of the data set, we're back to just averaging you out to everyone in the population. So to the extent that looking at a smaller, more similar group of data helps us predictively, if we spread that out too far, we lose that predictive power, and we're averaging everybody out. So the cool thing is the approach is very similar, and scikit-learn is known for having designed itself to be reusable in a variety of ways. And so in this case, we have our train test split. We can split up the data. So this is going to randomize this. In particular, you can see here, the irises are ordered. They're sorted based on whether they are setosas, versicolors, and virginicas. And you can possibly see that there would be a problem if I trained off of the first 2 classes and then I tried to test off of the final class. That would not produce very good results. So one of the other things that the train test split is doing here is shuffling the data up, and before it takes the sampling. We're not telling it percentages to use. I think it uses 80-20 by default. I could be wrong about that, but it's going to split the data up after randomizing it. We're then going to create a k nearest neighbors and classifier, and we're going to set k to be 5. So we're going to say the 5 closest neighbors to you will have influence on determining what you are. So that seems like maybe a pretty good combination. 1 maybe gives too much power to the thing that's closest to you, but if k gets too high, we lose the capacity to make predictions. So the classifier is initialized here. The training happens here, right? So fit is the training step again. And you can tell that unlike k-means clustering, which just looked at the data itself and then sort of shoved it into pockets, depending on how many things you look for, here we're actually trying to find the relationship between the inputs and the outputs, which is why it does a better job, right? It's actually looking at the data and going from there. So we're going to fit the data, and then we're going to make predictions off of our test data, and we're going to measure the accuracy overall of the visualization. I'm sorry, of the learning. And you'll notice this is pretty good, right? Right out of the bat, we see a 97.4 accuracy in predictions. Now, it's not particularly surprising because the data set is a very clean data set, and that's one of the reasons why it's being used. But the results are still quite good. So using a k nearest neighbors clustering algorithm with the data from the iris data set has done a pretty good job. Now, one of the things that you want to do is to make sure that the order in which we are selecting the data doesn't impact the quality of the training. So we're actually going to go through that process again, but now we're going to do it 10 times. And each time it's going to pick a different set of the data to train off of and test off of. So roughly, imagine we're going to take the data set, we're going to break it up into 10 blocks, and then in each block, we're going to have 10 runs of the data, shuffle it maybe 10 times, and a different portion will serve as the test data each time. So if the order in which we select the data has impact on the learning process, that's another sign that things are not as good as we think they are. So this is called a cross-validation. We're doing 10 splits, and if we average out the results, we see that on average, they did 97% accuracy across the board, which is very similar to what we saw before. So that seems like it's generally a good, stable approach on a relatively clean data set. So it's not always going to be the case, but we measure the accuracy of linear regression predictions by looking at how far off the predictions are numerically. We measure classification predictions by measuring how well did we do in predicting the outputs. If the majority of the irises were setosas, and I just said, oh, and I knew that, then I could just always guess setosa, and not knowing anything about the data other than that relationship, I would look pretty good from a prediction perspective, at least when setosas were concerned. So that's the kind of thing that we're trying to avoid. We're trying to avoid looking like we're doing better than we are. Often that comes from overfitting, but it can come from problems of how you slice the data up as well. So we are getting towards the end of our time. There are some other things that we can do that I encourage you to explore. There are some other Reactor sessions about using Python and NumPy if you need some help with that. But in this case, we're going to create a list of values of k from 1 to 25, and then we're going to rerun our k neighbors classifier to measure the impact of this hyperparameter and see how well it does. So for each k, we're going to run our cross-validation tests. So rather than doing this 10 times, we're now going to do this 250 times. And this is going to help us decide what are the best combinations in the training process. And we see that a k of 13 gives us the highest score. So that says if you factor in the 13 closest elements in the training data set to determine the classification, that gives you the best possible score. So what we have done is we have now explored a data set. We have found a way of making predictions based on the physical characteristics of the irises, what class do they belong to. We've then evaluated a particular use of that in the form of the k of 5. and we saw that it did pretty well, 97.7. But then we ran our tests again, varying the range, turning the knob from 1 to 26, and we can see that doing so allows us to find the best possible combination. Now, that doesn't mean that's always going to be our accuracy. It just means, based on what we've seen, if that's a good sample, then this setting gives it the best possible chance of being accurate. As the data changes, you may notice that you need to tweak that knob in different ways, right? So just because a model is doing well now on the data that you have available now doesn't mean it's going to continue to do well. So you're going to want to periodically evaluate whether the accuracy numbers are going up or down. And if so, you may need to retrain on the new data. That just means if you're training on sales data in your first year as an organization and comparing that to training on your sales data 10 years later, those early days are not going to help you predict 10 years in the future because things have changed so much, right? You have established customer bases with recurring revenue, and those things just didn't exist in the early days. So there are new influences on the shape of the data. Those you'd have to periodically revisit to figure out what those are. So what we've established is, a little bit of the process, a little bit of the ways that you can analyze the data, ways of analyzing the ways that you analyze the data. So having some sort of meta-analysis in the process, and doing so then helps you get a sense of whether you are actually learning from the data and generalizing well to additional population bases. How you cut the data up, how you collect the data, the knobs that you use to set on the parameters for the model all have the potential to impact the quality of the results. Now, one of the things that we can do is we can visualize the data directly to see why the clustering did such a good job. The problem is we have 4 values, right? We have sepal length, length, petal length, and petal length. And generally, we don't do well with visualization above 3. So oftentimes, what you'll do with your data is to reduce the number of dimensions. Now, this is a mathematical relationship coming out of the world of linear algebra. If you want to know more about it, I encourage you to look up principal component analysis. But it's basically saying for every dimension that you ask for, which vector in your multidimensional space carries the most variance, most of the predictive variance. Remember when we did the R-squared score for the linear relationship in the body size to brain size? That was a measure of how much of the variance in the output is predicted by the input. That's conceptually kind of what's going on with a principal component analysis decomposition. You're saying, I want to use fewer dimensions potentially to represent the data. So I want to know what vector has the most variance on it. That's going to carry the most information for me. So in this case, we're going to go from 4 dimensions down to 3 principal components. And we specify that by using a PCA. So this is a unsupervised learning transformation. We're going to go from 4 dimensions to 3 dimensions. And we're going to do that by doing a fit and transformation of the iris dataset. So that has 4 dimensions. We wanted to find the 3 most significant vectors in there. They are orthogonal to each other. So how much in this dimension, then how much in this dimension, and then how much in this dimension, and then how much in the 4th dimension, which we can't visualize. But we're going to do that and then actually transform our data through. But that now gives us 3-dimensional data that we can use to visualize the iris dataset. And so we're doing a scatter plot of the reduced data set, dimension, all the rows, dimension 0, all the rows, dimension 1, all the rows, dimension 2. and we're using the target value. So whether it's a setosa, a virginica, or a versicolor as the color selector, notice we see clumps of data. Those clumps exist in the visualization of how the dataset spatializes. Obviously, we can't do that in 4 dimensions, so we do this transformation down into 3 dimensions first. But hopefully this explains why the classifier was able to do such a good job in finding the clusters. If these clusters were closer or more intermingled, then other transformations in the data would probably have to take place before it would do a good job. But that's one of the reasons why the iris dataset is used for this kind of early instruction, is because it produces good results, and it's easy to see where that relationship is coming from. I did some training for a large cloud company, and early feedback that I got from somebody who took the class was it was too depressing because none of the examples worked when we were first learning. So I now see the importance of having a good, clean data set that makes it easy to see what's going on. So I hope this was interesting. This was a quick introduction to the interrelationship between data science and machine learning. We're using the Python language. It's got a very clean syntax. When it's accelerated through the use of NumPy, it actually becomes quite decent, particularly on modern hardware, for individuals to explore and visualize data. Not necessarily the runtime or the programming languages you would use to take into production, but usually the models that were created with scikit-learn can be serialized out and read into other frameworks. So 2 of the learning tools that we explored were linear regression, where we're trying to make a numerical prediction of the outcome, and classification, which is a way of allowing us to look at data sets and find similar elements within the data sets. We used supervised learning for most of those, where the inputs and the outputs, the relationship between those are what's being discovered by the learning process. We also showed an unsupervised learning activity, just saying, look at the data and try to put it into categories on your own. And it didn't have the feedback loop that the supervised learning does, so it's not able to learn quite as well. We showed how visualization can be used to help you explore the data, but also to measure the success in the predictions, like we saw with the red lines. And we saw a variety of analytical techniques for slicing the data up so that you don't accidentally train on one type of data and not on the other. We saw the benefits of slicing the data up into training and test data to avoid overfitting, or at least to be able to detect when we're overfitting. And then we saw a variety of model evaluation tools like R-squared for the linear regression, the confusion matrix, and accuracy scores for, we didn't do a confusion matrix, but the accuracy scores for the classifier. So I don't know if there are any questions, but.
Thank you, Brian, for today's workshop. And yes, we have some questions.
Okay.
The first is from Simon. And Simon is asking, how do we measure the bias during a linear regression prediction?
So specifically, sorry, it's still early in the morning. The bias in
a linear regression prediction. This was early on the session. It was sent. I think it relates to how much that data is tending towards a certain prediction.
Right. So the there are various approaches. I'm sorry, I'm a little fried right now. The metrics capabilities in scikit-learn have other ways of measuring the influence of the various elements, how much each of those components contribute. The coefficient strength is one of the ways of measuring that. But then looking at the quality of the predictions, we've got the R squared and other ones in there as well. So I'm not sure that I'm going to do a better job right now on that. Are there any other questions?
Yeah, so there was a question also on the possibility to converge a linear regression to semi-supervised algorithm. For instance, coefficients are evaluated by other, I think, algorithms. Here we use the short for it.
Yeah, so there's a lot more that you can do with linear regression. You could measure the interrelationship between features by, calculating ratios. You can square the results. So there's a lot of things that you can do. It's still linear with respect to the relationship, the coefficients to the features, but then you could also analyze those coefficients themselves and use those as the basis of additional training. So there's these additional styles of learning, transfer learning, semi-supervised learning that fall out of the kind of meta-analysis. You can get a model up to a point and then use that as the basis for another model. So
one more question from Mark. He's asking, what are you using for graphing?
This is matplotlib. And it is one of the most common Python libraries. I'm using the Anaconda instance as the basis for the Python engine. So that comes with it installed, but any Python installation, if you use the pip or the package management tools, you can install matplotlib, and it's a fairly nice, efficient way of using it. It's discussed at the beginning of the notebook right here about it. If you go to matplotlib.org, I believe you can find out more about it. There are other frameworks. Seaborn builds on top of it, and it's kind of an opinionated use of matplotlib. So with less code, you can produce sort of more featureful results. But matplotlib is sort of the de facto visualization library for at least scikit-learn based visualization.
All right, that was it with the questions. Thank you, Brian, for today's workshop. It was great to see all these applications of linear algebra and all the topics that some of us might have seen in college, and today it has all these wonderful applications into data science, machine learning, and all these let's say future technologies and applications that are opening to every one of us. Thank you for all the community members that attended today. Just a quick reminder, we're doing a survey to help us understand more the topics that you would love to see at the Reactor. So please spend a minute to give us that feedback. Today's session is recorded, and we will get it on YouTube very soon. I put the link to the channel in the Q&A tab, so you will have it there. And that's all. Stay connected with the Reactor. All the programming is free, open to all. We're doing a series of workshops every week, and there are other sessions also that we're hosting on a local basis across all the Reactors. As I said, we have in Abu Dhabi, in London, Stockholm, and across the world. So please be part of the communities there. Connect to the other members in these groups. Thank you so much, Brian, again, and goodbye, everyone.
All right. Thank you.